Hi everyone. So today we're going to start a new section called lines and planes, and we're going to be using some of the vector stuff that we learned earlier. Okay, so we're going to start off with lines in Rn. Okay, so we're going to first look at a simple example in R2 that you're familiar with, and then we'll extend this idea to any dimension. Okay, so let's start in R2. Imagine we've got the axes like this. We've got X and Y, and we've got some line in the plane, something like this. Okay, what we want to do is try and describe this line, but not using y equals mx plus c, like you've learned before, but using vectors. Okay, so we want to describe this line using vectors, not y equals mx plus c. Because we'll see that y equals mx plus c, that works in 2 dimensions, that's fine. However, if you want to describe a line in higher dimensions, like R3 or R4, we need a different way of describing it. Okay, so we're going to do that using vectors. So the way we do that is we imagine that this line is passing through some special point. So let's say the point is over here. So you pick a point and then you say, this line going through that point, I want to describe it using a vector. Okay, so the way we do that is we imagine a vector that lies along the line, something like this. Okay, we're going to call that vector v. And if we scale this vector, we can then reach any point along this line. Because remember, scaling the vector just means making it longer or shorter. So if we look at the vector 2v, that's going to be something like this. It's going to be from this line all the way to the end here. That's 2v. And then we can even look at minus v, which will then be in the opposite direction because all the components have been reversed. So if we go here, this is minus v. So with appropriate scaling, we can reach any point along this line. So v ends up over here, 2v ends up over here, minus v ends up over here. And in fact, with any multiple, you can reach any point along this line. So we can reach any point along this line using a multiple of v. Okay, and remember, v is a vector that lies along the line. Okay. Now, what we need to try and do is think about this vector, okay, going here, but we also need to consider the starting point. So what we do to reach any point along the line is we start from the origin and we move from the origin to this point using this vector. Okay, we call that vector R0. And if we take this R0 vector and we add our scaled version of v, then we reach any vector along the line using our vector addition rules. Okay, so just as an example, if I take R0 plus 1 times v, then this is going to look something like this. We've got R0 going like that, going in that direction. V is going in this direction. So R0 plus v, R naught plus V is going to be this vector along here. So that's R naught plus V. Okay, which is going to be this vector over here. And we can see that reaches the point that we wanted. Okay, if we do something like R naught minus V, okay, so let's do it on the side here, R naught minus 1 times V. Okay, we've got R naught going along here. We've got minus V along that way. If we add them, we end up over here. Okay, so again, this is R naught. This is V. And this is going to be R naught minus V. Okay, so with appropriate vector addition, we can reach any vector along this line. So first we go from the origin to this point labeled blue with the red vector R naught. And then if we add a multiple of V, we end up anywhere along this line. Okay, so in general, we have R as a function of T is equal to R naught plus T times V. Okay, so R naught, this is a vector that points to some point along the line. And V, this is a vector that lies on the line. Okay, and T, that is what we call the scaling parameter. So if we change T, that means we're moving along the line. Okay, so let's have a look at an example. We'll first do an example in R2, and then we'll do an example in R3. Okay, so find the vector equation for the line that passes through the points P, which is at 0, 1, and Q, which is at 2, 3. So we've got these 2 points in R2, and we would like to find the line that passes through them. Okay, so let's draw this in a Cartesian plane just to see what's going on. Okay, so we have X and Y. Let's do P first. So X is 0, Y is 1, so it's somewhere over here. So that's P, and then Q, that's at 2, 3, so that's somewhere over here. Okay, and we would like to find the line that passes through these 2 points. So it's going to be something like this. Okay, so first we need our R naught value. So that is just any point that is along this line. So we can choose the vector that goes to P, or we could choose the vector that goes to Q. It doesn't matter as long as it's on the line. So let's choose Q. So from the origin to Q, we draw our vector like that. Okay, this is going to be our R naught, which is just a vector that points to any points along the line. Okay, so that's the first thing. So here R naught is given by 2, 3. Okay, that's our vector that points to Q. Now we need the vector V that lies along the line. Now remember what I said last time. If we take the vector that goes to Q minus the vector that goes to P, we will get the vector that goes from P to Q. We can get this vector here. Okay, so that is a vector that lies along the line. Or we could do it the other way. We could do the vector P minus the vector Q, and then we would get a vector that lies along the line, but in the other direction. Okay, so it doesn't matter which way you take it, as long as it's along the line. So let's say V is going to be the vector Q minus the vector P. Okay, so I'm doing the end of the arrow minus the start of the arrow. So that's going to be 2, 3 minus 0, 1. That's going to be 2, 2. So that is our vector that goes along the line. Now, if we want to reach any point along this line, we can just say that R of t, so that is any point along the line, okay, R of t is given by R naught plus t times v. Because remember, we scale v, and that moves us along the line. So this is going to be 2, 3 plus t times 2, 2. So if you provide a value of t, that will give you a point on the line. Okay, so this is the vector form of the line, but there are several other forms that you can write as well. So let's just go through them. Number 1, the vector form. So this is writing R of t is equal to 2, 3 plus t 2, 2. Okay. Now, since these are vectors, we can add them together to get a new vector. Okay, and then that gives us our second form, which is parametric equation form. Okay, so I'm going to take the vector form and then add the two vectors together. So R of t is going to be 2, 3 plus t times 2, 2. So we can write that as 2, 3 plus 2t, 2t. So I just multiplied the t inside. So that's going to be 2 plus 2t and 3 plus 2t. But we know from our work with vectors that the first component, we call that x. So this first component here, that's x. The second component, that's y. That's what we call it. So we could write this as x as a function of t is 2 plus 2t, and y as a function of t, which is 3 plus 2t. Okay. So this word parametric, that relates to t. So t is called the parameter. So for parametric, we say t is the parameter. Okay, and parametric equations, sorry. So we get an equation for each component of the vector. So for each component, we get a separate equation. So here, since we're working in R2, we get these two equations, one for X and one for Y. Okay. And number 3, we have the symmetric form. Okay, so all of these are just different ways of writing out the same thing. So I've got the vector form of writing it out, parametric equations form, and the symmetric form. Okay, so depending on what you're trying to do, one of these forms could be better than the other ones. Okay, so for symmetric form, what we do is we take these parametric equations and we write them in terms of t. So firstly, we have x is equal, I'm going to just write it as x. I'm not going to write it as a function, just to make it simpler. So we have x is equal to 2 plus 2t, and we have y is equal to 3 plus 2t. Okay, and you see both of them depend on t. So what I'm going to do now is solve all of them for t. So for x, we're going to have x minus 2 is equal to 2t. So x minus 2 over 2 is equal to t. Okay, here we have y minus 3 is equal to 2t. So y minus 3 over 2 is equal to t. Now, both of them depend on the parameter t. So what we can do is make them equal to each other. Okay, because they're both equal to t, so they're both equal to each other. So we can write x minus 2 over 2 is equal to y minus 3 over 2. Okay, and we just leave it like that. That's called the symmetric form. So you see in the symmetric form, we no longer have the parameter t. Okay. Now, again, all three versions here are identical. So they say exactly the same thing, but maybe you have an application where one form is easier to use over the other form. For example, if you're doing like a physics problem with something moving along a straight line, maybe you would use the vector form or the parametric equation form. You might use one of those two. Okay, so like for a physics problem, the symmetric form might not be helpful. Okay, or if you're making like a computer game, maybe the parametric form would be better. Okay, because if you're coding it, maybe that one's better to use. Okay, but all three say exactly the same thing. It just depends on what you're using it for. Okay, so this example was in R2. Let's have a look at an example in R3. Okay, so find the equation of the line that passes through the points P, let's say 0, 1, 0, and Q, let's say 1, 2, 3. Okay, something like that. Now, since this is in R3, it would be a bit more difficult to draw, okay, because you would have 3 axes and you have to try to label the points. So we won't draw this version, but we'll just show the calculations. Okay, so firstly, we need to find a point that lies on the curve. Lies on the line, sorry. Need a point on the line. Okay, so again, you can choose P or you can choose Q. It doesn't matter which one you pick, as long as it's on the line. So let's pick P. Okay, so R0, that's a point on the line. We're choosing P, so that will be 0, 1, 0. Okay, and step 2, need a vector that lies on the line. Yeah, and the easiest way to do that is you take the vector at P minus the vector at Q, and that will give you a vector along the line. Or you could do Q minus P, and then that would just be the reverse. Okay, let's do Q minus P. So V would be the vector at Q minus the vector at P. So that would be 1, 2, 3 minus 0, 1, 0. Okay, so Q minus P. That's going to give us 1, 1, 3. Okay, so that would be a vector that goes along the line. Okay, so it would be something like this if you wanted to draw a rough picture. So we've got, let's say, P over here, Q over here, and let's say our origin is over here, origin O. We've got our R naught that goes to P. And then we've got our vector V that goes from P to Q. So that's V. And if we take scalar multiples of V, that will give us any point that goes along this line. So if we multiply V by 2, then we move twice as far along the line here. We'll end up there. If we take minus V, then we go in the opposite direction and we end up somewhere here. So here would be 2V, R naught plus 2V. Over here would be R naught minus V. Okay, and then you would move anywhere along that line. Okay, so let's put everything together. R of t is equal to R naught plus our parameter t times V. Okay, R naught, we said that was 0, 1, 0. Plus t times V, which is 1, 1, 3. Okay, so this is our vector form. Okay, we can leave it like that. Just make a little note, this is vector form. Okay, so let's do the other forms just to complete the example. So that's number 1. Number 2, let's do the parametric equations form. Okay, so remember what we do for that. We add up the vector to get a single vector. So R of t is going to be 0 plus t, 1 plus t, and 0 plus 3t. Okay, we can simplify that to just t, 1 plus t, 3t. And again, we just identify the components. So the first one, we call that x. The second one, we call that y. The third one, we call that z. So this gives us 3 equations for the 3 components. So x of t is just t. Y of t is 1 plus t. And z of t is 3t. Okay, and then this set of equations, those make up our parametric equations. And again, t, that's our parameter. Okay, and then the third one, that symmetric form, let's do that quick. Okay, so we write out our equations. So we have x is equal to t. So remember, x is a function of t, but I'm just going to write x for just to make it simpler. Y is equal to 1 plus t, and again, it's a function of t, plus z. So z, that is 3t. Now we solve for t for all of them. So x is equal to t, that's easy to do. Y is equal to 1 plus t, we can write y minus 1 is equal to t. And z over 3 is equal to t. So we see that all of them are now written in terms of t. Now, since all of those equations are equal to t, we can then just make them equal to each other. So x is equal to y minus 1, which is equal to z over 3. Okay, now it looks funny having two equal signs in the one equation, but that's just how we write it. Okay, you can just leave it like that. Okay, and just denote this.
Sorry, sir, can you please explain the second form again?
Parametric equations.
Yes,
Okay,
sir.
sure. So what we do is we take the vector form and we add it together to get a single vector. So we take the vector form, which is r of t is equal to r naught plus t times v, and we write it as a single vector. Okay, so here we took this component and this component and we added it together there and there. We took this component and this component, we added it together here. And we took the last component, so there and there, and we added to get that. So remember how we add vectors, we just add them component-wise. So the first component of the first vector plus the first component of the second vector, we add it. So we get 0 plus t, so that's 0 plus t, which is just t. Then we have 1 plus t times 1, so that's just 1 plus t, so 1 plus t. Then we have 0 plus t times 3, so that's 0 plus 3t, that's just 3t. Okay, so we write it as a single vector. So here we've got a single vector. Then we just label the components. So the first component is going to be x as a function of t, because remember, r of t is x, y, z. We did that right at the beginning. First lecture, we did this stuff. So the first component is x. So x equals t because of the first bit here. So that gives us our first equation. The second component is y. So the second component here is 1 plus t. So our second equation is y equals 1 plus t. And then our third component is 3t, but that matches up with z. So that gives us our third equation, z equals 3t. So at the end, we should get 1, 2, 3 equations because there are 3 components. Okay,
Thank you, sir.
does that help?
Yes,
Okay,
sir.
awesome. Cool. Okay, and then the symmetric form, yeah, so you just make them equal, and notes again, there is no parameter t. Okay, so in the symmetric form, we don't have any t parameter. Okay, it's just in terms of the variables x, y, and z. Okay, so this was in 3 dimensions. Of course, you could do it in higher dimensions as well. So if you want to try for R4, something like that, if we have P is 0, 1, minus 1, 2. So now we have 4 components. And let's say Q is 1, 2, minus 1, 3. Again, 4 components because of the R4. Then you could find the equation again. But here, there's going to be 4 components. So for your parametric equations, you would have something like x of t y of t, z of t, and maybe the last one, let's call that w of t. Okay, because there's 4 components here. So you got your x, y, z, w, for example. So it doesn't matter what you call that last one. Let's just say w. So we get 4 parametric equations. Okay, and then that's the same thing for any dimension. So if it's 6 dimensions, then you're going to have 6 parametric equations. Yeah, here there are 4 parametric equations. Okay. So we're going to leave it at that for today. Tomorrow we will then look at the examples on finding equations of planes. So these were lines through Rn. We can also have planes through Rn. So that's something like this. Okay, where you've got like a sheet of paper, for example, in 3-dimensional space. So this is, you can think of like a piece of paper, but it's not finite. It's an infinite piece of paper. So infinite plane in Rn, and we can find an equation that describes those points along here. So this particular point, let's say that's P. This point, satisfies the plane equation. Okay, so points on the plane will satisfy the plane equation. Points outside of the plane will not satisfy the plane equation. Okay, and the goal for tomorrow is figuring out how do we get this plane equation here. Okay, but we'll save that tomorrow. Save that for tomorrow. Okay, if you have any questions, please just email me or can post your questions on the WhatsApp group. And remember that the tutors are also available for help as well. Okay, I'll see everyone tomorrow. Bye.